Hi there. So a great question came in to support about this older post from 2015 about freezing heat release rate in PyroSim, and if there's a more elegant or better way to do that now through PyroSim directly without having to add a bunch of additional records, FDS records, to the additional records section in the record view of PyroSim and manually entering these in. And back in 2015, PyroSim did not support these sort of freeze devices and some things like that. And it actually does now. So this video is just to give a little update to this older post. And I plan on rewriting or making maybe a new post that refers back to this, but with some updated information. And this video will likely be a part of that post. So anyway, let's talk a little bit about this. So the freezing heat release rate, essentially what you're trying to do is you're trying to say, I want the heat release rate to grow as a function of time. And normally that would be just a normal burner ramp. So you would say, at 0%, 0.0% of the fraction. And then as it grows, as time increases, then the fraction of the peak heat release rate is released until it reaches its peak. And you control that with a ramp function, essentially with time as the input. Well, what you can do now is you can say, okay, what if I want the heat release rate to stop growing when a certain condition occurs and essentially stop increasing the value of time that's the input to the ramp function itself that generates the heat release rate. So that's essentially what this post is talking about, and you can read this older post and the newer one that this might be a part of. But let's take a look at the new settings in PyroSim to enable this to take place. And you'll notice now that my record view, I don't have any additional records, right? So let's take a look at how we do that. So the first thing that we need is we need some set of sensors that would be input to a control that we will use to stop time. So in this case, it's a very simple one. We just have a single temperature value with a set point of 200. So this is temperature quantity. And when this temperature sensor, when this device reaches 200, it will trigger, it will change state. And so you can see that here. And now because we have set point checked, this enables set point checked, this becomes an input. This can be used as an input to other controls. So the other device that we need is we need a time device. And usually to make a new time device, in fact, before I show you that, let me just show you in devices. You can say new time device, and this is how they typically look. You'll have some name of the device, what quantity that it's measuring, and what its output will be is time. Okay, so now in this case, we're not going to set a set point here, but we can make a control that will freeze the output of the time device at whatever value of time it is when that the input device changes state. So we have our time device, and let's take a look at the actual one that we have here. And so now in PyroSim, we have this freeze output option, and by default, it'll show new or never, and it's set to never by default. So you can make a new one, and let's go take a look at this. As soon as you make a new one, I can click on that. It'll name a control, and you would want to name it something. So let's just go take a look at this control real quick. We'll call it freeze time. And essentially it'll be a detector that will freeze, and we want to freeze time, right? So this kind of gets hooked up when you do it through this path. If you say new, it'll freeze time. So it's a detector that freezes time when something activates. So in this case, it's our temperature sensor. So we would need that temperature sensor to exist before we can do this part, because we want to be able to pick input devices, right? So in this case, it's just the one temperature sensor. And when that activates, it'll freeze time, which is this device, okay? So if you're following me so far, we've now created a freeze output that will freeze this time device when temperature activates. And you can see that down here. So the device name is time, it's measuring time, and outputting time, essentially, if you think of it that way. And that's simulation time. And then it doesn't matter where it's located, and as long as it's within the domain somewhere, so 000 is fine. You can kind of see it down in the corner here. And then you'll see this no update control ID equals freeze time. And so we're linking to this control freeze time as the input to the freeze function here, okay? That it'll stop updating when freeze time is true. And then the device that we are sensing is temperature, and it's measuring temperature with a set point of 200. Okay, so now we have our kind of our control setup that will freeze time, right? By default, we would have this heat release rate per unit area and a custom ramp, right? And if we edit the values of this, typically it's set, the function input is set to time. But in this case, we actually want to connect it to this time device, not to the device, temperature device, because that would be the input to this table. The input side would be temperature, but we want to do it to time. And so now what the input here is, this time, is not simulation time, but the time value output from the time device, which is over here. And when that freezes based on the state of this control, then it will just continue to pass whatever the value is at the time of that state change. Okay, so it may not make it all the way up to 50 seconds because maybe the temperature device activates at 30 seconds, 35 seconds, whatever, right? Some number, and then that's the number that would be passed into this this linear interpolation function. So it's going to go from 0 to 100%, from 0 to 50 seconds, and now you can imagine if I come in at 35, then it would be 35 over 50, which would be sort of the fraction, right? That would be passed in here. That's the value that would be in this table. Now that fraction is actually a fraction of the peak heat release rate. So if this is 1,000 at peak kilowatts per square meter, then instead of it would be somewhere between 0 and 1, which is 0 to 100%, determined by the input to this function. Hopefully that's clear. So now we've set this to device time, not simulation time, but our device time. And we'll just kind of back through that again. So here you see device ID is time for the input to the ramp. Okay. And so just to think back through it, we have let's kind of start with fundamentals. So we have a temperature sensor that's got a set point. We have a time device with a freeze output control called freeze time that will freeze the value, the output. So we're freezing the output when temperature activates. And that generates, this time device actually generates the input to our heat release rate ramp, controlling the value that gets passed in to determine what fraction of the heat release rate should be used for the fire. Okay, so hopefully that's all clear. And now if we run this case, what we'll see is we'll get the heat release rate, and you notice it's coming up, 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 and then it freezes, right? It doesn't continue to increase. And if you remember that the kilowatts, it goes, in this case, it's the area of the vent, I believe, is like 0.4 square meters. So it wouldn't quite get up to 1,000 kilowatts per square meter because it's just less area. But you can see that it stopped quite early, around 5 seconds in the growth, between and originally it could go all the way up to 50 seconds. So if we were to not have this freeze function, this line would just continue up until it hits the peak of 1,000 kilowatts per square meter, right? But it goes earlier than that. So let's then go take a look at our device results, and we can see our temperature sensor, right? So it's all over the place over time. But you notice, let's maximize this so we get a little more detail. So it's measuring ambient, then it starts to increase and then goes up and then goes up. And here's that 200. So the first time we hit it is about here. And if we take a look at that, it's just after 5 seconds. Okay. And to get a little bit more detail on that, let's take a look at the device results again. Sorry about that. And what we'll see here is in our time device, take a look at this. So this is the x-axis is actually simulation time. right? So it goes out to 20 seconds. The y-axis is the time output from the device, right? So if it goes up as a linear growth, right? It's like 1-to-1 all the way up to here. And then when that device activates, when that temperature device activates, it freezes time. And now it just is passing in this time value, whatever that is. It's just a little over 5 seconds, like 5.1 something seconds. Okay. And so 5.1 seconds is the input then to this ramp. So between 0 and 50, so it stopped at 5. So it's a very small fraction, and we can actually compute that. Let's take a look here at something. So if we kind of look at this formula, right? So let's go take a look and see where we can get this actual value, this 5.13, okay? But it's 5.13 seconds out of 50. That's the fraction of time, of the time that we get, to the peak of 1,000 kilowatts per square meter times 0.04 square meters, right? Or 0.04 squared, which is the length of the one side of the vent. So this right here should compute for us. We have the area times the peak heat release rate per unit area, and then the time input, or the fraction of this value, whatever that is. Okay, so let's go take a look and see if we can find the 5.13 now. And actually, let me cancel this. I'm just going to copy this, and we'll check this out. Okay, so I'll bring in a Google here, and I'll give it its equation, and let's see what it says. So 16.416 kilowatts should be our output, and let's just double check that that's actually what we get. So let's go back into our thermal results. We'll take a look at heat release rate. And if we were to draw a line through the noise, you can see that it's somewhere close to that value, right? So that's the connection there. Let me go back to here just to double check. 16.416 and 16.4 is probably right through the middle of that. So this is good. Now, the actual heat release rate that FDS computes is not the mass loss rate of fuel. So this is the mass loss rate of fuel over time from that burner. And you can see that that is a very fixed and solid value, right? Because it was frozen at a particular amount of kilograms per second. But the heat release rate is computed by the combustion calculations, and that depends on air and fuel mixture and turbulence and mixing and all of that stuff. So this can be quite dynamic over time, but behind the scenes, there's a fixed mass loss rate. So that's where this noise comes from, is just the turbulence of FDS, the actual like combustion calculations happening in the gas phase. But you can tell that, the ideal is somewhere around 16, and that's what we get. Okay, so that's the first part of this demonstration, and there might be a question about like, well, where does this data come from? Let's go ahead and take a look here in this control, or we can look in the device actually. So let's go to the device data, and if we take a look at this time column, I'm just going to switch this to numbers, okay, and watch this. So we scroll down in time, look at that, 5.12. There it is, 5.12 seconds. And it probably is, like, if we could extend this out, it's a little more than 5.12, right? But essentially that's the value there, right? At where it freezes. And as we continue forward in time, that value is the input to, let's go like this. So this exact value, that's the input, and it'll stay the same throughout the rest of the simulation. That's the input to that table, to that heat release rate curve. So if we come in here, you can think about this. If 5.12 is the time in seconds input that goes for the whole rest of the simulation, and that would determine this fraction. Okay, so that's the first part. That's the first part of this tutorial, right? Is how to do that, right? And you can see now that if we go to record view, let's take a look at that really quick, just to connect this structure and the inputs to FDS input. So here we have this control called freeze time. The function type is all. It will latch. That's true. That means when it changes state, it can't change back if the value goes below 200. Like whatever the state changes will be kept. The inputs to the control, in this case, is just one. It's that temperature device. And so even though it's a function type all, there's only one input. So if that activates, it's all true, right? All of them are true. So we have that control. Now we have our temperature device. It's measuring temperature with a set point of 200. So that's the input to this control. And then we have this time device that's measuring or outputting time. And it has a no update control ID of freeze time. So when freeze time is true, it freezes. It won't update the output anymore. And that's how we lock in the time input to the heat release rate ramp. And then the rest of this, like we can come down here a little bit, take a look at that ramp. So the ramp, fire ramp Q, is the ramp for that heat release rate curve, or for this burner. And the ramp here, fire ramp Q, from T0 to 50 has a fraction of 0 to 100%. And the device that it's actually using for the input to this first part of the function, right, to the first part of the table, is the device ID time. And now we can see how that can then be frozen by the activation of freeze time, which is determined by the activation of this device, which has a set point of 200 degrees Celsius. And that's it. The rest of this is just, you've got some open vents, and you've got a fire, surface ID fire, which connects to this on the vent, and we're measuring a slice of temperature. So it's quite simple, actually, once you kind of think about what you have, what you need, and how you can hook it all up, and the new capabilities within PyroSim to be able to use that as a freeze output function. So let's also now, there was another part of this tutorial originally that talked about multiple sprinklers. So like, what if instead of just a single temperature input, maybe we have a couple of different sprinklers that we want as the input. So if any of those sprinklers activate, then we want time to freeze. And this is the more typical, I think, use case for the freeze time device and freezing heat release rate is, I have some set of sprinklers in my model. I don't necessarily want to try to use the extinguishing coefficient to determine how many kilograms of water mass accumulate per square meter over time on the burner surface. I just want to say, I'm going to make the assumption that if any sprinklers activate, then wherever the heat release rate is at that point, we're just going to hold the heat release rate. Like, we're not going to diminish it. It won't continue to grow. We're just going to assume that the sprinklers can suppress and maintain that same state, that same heat release rate. So that's the most common, I would say, a more common use case for this feature. So let's take a look at that. It's very similar. You'll notice that we still have our time device, okay? And the output for that is, or what we're using, the control that we're using to freeze that output of time is this freeze time control. Now, if I click on this link, it'll open that up. And again, it's very similar, right? It's a detector that's going to freeze. So we're going to freeze that time device when any of these links activate. So if we click on this, we can actually see that there's both a link and a nozzle device, right? So the nozzle is what's spraying, the link is what's measuring temperature. And the way that the sprinklers tend to be hooked up is if the link activates, then the nozzle activates. So there's a control that connects those two. But what we really want to do is connect ourselves to the links, right? Because those are the actual sensors that when they activate, we're going to assume the sprinkler activates. Now you could instead, if maybe there was more to it, right? Maybe another control that required multiple links to activate before the nozzle or something like that. You could also tie yourself to the nozzle and say, when the water sprays is when I actually want to activate to freeze time. And that's a little bit different way of looking at it. That might actually be a little more safe in this case, is to connect to the nozzles. Okay, because then it's actually when water is spraying and not when some input devices change state, because there could be more behind the scenes there, like a delay time. That's a great example. You could have a dry pipe delay. So the link activates, but the nozzle doesn't actually spray for like 30 seconds or 10 seconds or something, right? Well, you would freeze time at that point, but the water is not actually even spraying yet. So hooking yourself to the nozzles is probably better. And then if you wanted a little more flexibility, right now it's an any of, which is an any function, right? So when any of those activate, if you wanted it for all of them have to be active before you freeze time, or you could say when at least one of them. Or if you had, maybe 10 nozzles, and you could say, well, when at least two of these activate, then we'll consider it to be suppressed. There's a no more than, which doesn't really make sense, or exactly some number. So when exactly two of the set, or exactly one in this case, and you can change that as well. You can say how many need to activate before you freeze the heat release rate. So in this case, we're going to go back to any. So just it could be when any one of these activate, then do it. And we're not going to put any kind of a freezing delay in there. Okay. So there's our control. And now we set up these sprinklers like normal. These are just normal sprinklers, right? They have a spray model, they have a dry pipe, no dry pipe delay here. That's where that could get messy if you're hooked up to the link. And the activator of the sprinkler is the temperature link. And in this case, it's the default, right? We're just using this default link. You may have other links you've developed, but let's take a look at the default. It has some activation temperature and an RTI and a C factor, right? So when this activation temperature is met, 68C, based on the input, based on the calculation of its actual temperature, based on this RTI value. When that's met for any of the sprinklers, then heat release rate will freeze. And if we take a look at the data from this, this is indeed what we see. So sprinkler 1 has over time, a temperature measurement. Sprinkler 2 has a different path, right? Because they're in different positions relative to the fire. So sprinkler 1, I would say sprinkler 2 actually looks like it's the one, and as we see, it's right close to the fire, right over it. So it definitely has a higher reading earlier, and it actually ends up being the one that triggers the value. And if we look at this, we can see 60. Here, let me zoom in. We see 60 degrees, and just like 65 would be in here, and we're looking for 68, so it's probably somewhere in here just before it peaks out. And we actually see the activation kind of changes temperature, doesn't it? Kind of levels it out here, so gas temperature changes a bit. But you can see that around here, and it's around 35 seconds or so. So let's take a look back here, and we'll go to the freeze time device actually, and look at that. 35, close to 35 seconds, probably just shy of it, is where the seconds value gets locked to around 35 seconds, right? So we see that here, and then it just continues on over time as that same input to the burner. And sure enough, in our burner, we have an edit values. And look at that. The device, freeze time device, is the input between 0 and 60 seconds. So it's about 50% or so, right? Because it'd be 30 seconds would be half between here. So around 50% of the heat release rate per unit area. And we can see the area here. Let me hide that so we can go take a look at this. If we take a look at the geometry, you can compute the area of that, right? And then use that as your function, and it should come out to the same heat release rate, which is now, it takes a while, right? It has all this time to continue to grow. As the turbulence and everything becomes more dynamic, the heat release rate becomes a little bit noisier, but you can see it level out and maintain right around the 35-second mark when that activates. So hopefully that's helpful. You can see how multiple inputs, and it doesn't have to be sprinkler links or nozzles. It could be heat detectors or sensors or whatever, right? It could be anything. Ultimately, you just have to remember you need some time device that's outputting time that freezes its output when some condition is true. And that should give you this control over your heat release rate. So hopefully that's helpful. If you have any questions, please let us know. You can always email support@thunderheadeng.com. We'll be happy to help you out. Thank you.